All right. So let's take a look at halogenation again. So yesterday we said we can treat an alkene with elemental bromine, and we can get bromine to add to each carbon of that carbon-carbon double bond. So in this case, we said that the experimental observations showed that the bromines add anti to one another, meaning one's going to be on the opposite face as the other. So one would be a wedge while the other is a dash. And you have to watch out for getting a mixture of enantiomers if you're forming something with new stereocenters. We said first that students like to show this mechanism that I showed as option 1, where you go through a carbocation. This feels intuitively right. However, experimentally, we know that this mechanism is incorrect because we don't get 4 products out of this reaction. We only get 2. And we know that experimentally, we only get the anti-addition products, where we get those wedge-dash combos, not both wedges and not both dashes. That means that this entire mechanism, as shown, is wrong. So we can just cross that out and say that that mechanism is not going to work. That left us with option 2, where we said instead of going through a carbocation, we actually go through this 3-membered ring where you have this bromine bridge with a positive charge. I did forget to name these the other day. These have a special name. These are called bromonium ions. And bromonium ions look strange because it's a 3-membered ring. We know that it looks unstable, and bromine doesn't like to have a positive charge. But as far as we can tell as experimental chemists, this is the way the mechanism proceeds most of the time. We know that if we went through the carbocation mechanism, that we would get many more products and we would get different stereochemistry out. So as far as we can tell, this is the best explanation. So this is a better mechanism that explains the observed products. Does that make sense? So like I said, is this absolutely 100% the right mechanism? Maybe, but we just don't have evidence that it's wrong, right? So this is the best case scenario that we've been able to come up with as chemists. Yep.
Is this called halogenation?
This is called halogenation.
And then in the lab, I think we use something similar to oxygen, right?
Yeah, so we'll talk about a variety of these 3-membered rings. You're talking about oxygen in a 3-membered ring. Those are called epoxides, and we'll actually have a whole chapter on those. So there's a lot of different chemistry that involves these highly strained 3-membered rings where there's a non-carbon atom in the ring system.
Is there a common name for this? Like what happens with this mechanism?
This is just...
When you have a double bond and it creates a 3-membered ring,
It's just called an addition reaction in general. So anytime a double bond's attacking something else that's an electrophile, it's just a generic addition reaction. Yep, good question. All right, the next one is kind of a variation on what we've been looking at. This is called acid-catalyzed hydration. So again, what I like to do is show the experimental observation first, and then we'll try to propose a mechanism. So experimentally, you can take an alkene, you can add water in, and then what you do is you can take just a tiny, tiny bit of catalytic acid. And so I'll show that as H plus in brackets. And I'm going to write catalytic underneath, so cat. What does it mean when I say catalytic? It gets regenerated throughout the reaction. Do you need a lot of it? No, a pin drop could potentially get this to initiate and then proceed. All right, so when we mix these two together with catalytic acid, we end up getting an alcohol out. So now what we need to do is propose a mechanism that explains the formation of this alcohol. So let's do this. What's the fastest reaction in chemistry that we've seen so far? Does anybody remember? Acid-base chemistry. So if we've got all of these mixed around in solution, what do you think the fastest acid-base reaction is going to be? Yeah, forming hydronium, absolutely. So water will quickly grab this proton, and we'll just get hydronium. All right, so at this point, we've got our hydronium ion. And if we think about the dipole here, the oxygen's not happy with the positive charge, so it's going to pull electron density away from one of its hydrogens, right? So like we saw before, these pi bonds can act as a nucleophile because it's electron rich. And then over here, this can be an electrophile because it's electron poor. So with our classic arrow pushing, we can say our nucleophile is going to attack our electrophile and then kick off our leaving group. Just like we saw previously, we have a choice. Does the hydrogen go on the left and give us that? Or does the hydrogen go in the middle and give us that carbocation? Which carbocation is more likely, the one on the left or the right? The first one, why? It's more stable, it's a secondary carbocation. So just like we saw previously, that one's just simply not going to be observed. So I'm just going to slide this over. And we still have water floating around. All right, water, we said back when we were talking about SN1 chemistry, it's a pretty weak nucleophile, right? So in this case, water can actually add straight into that carbocation. This looks a lot like our SN1 chemistry. Okay, that gives us an intermediate where the water that added in, that oxygen, has a positive charge, right? Because it still has both of its protons on there. What do you think the last step's likely going to be? Deprotonation. So oftentimes when you do this reaction, we'll even write this over here, you have excess water. And this excess water is actually going to facilitate the proton transfer in your next step. So in this next step, water can grab this proton, clamp back down, give us our alcohol, and then like we said, our acid is regenerated, meaning it's catalytic. Does that make sense? All right, so this one is luckily pretty intuitive. Often students forget about the proton transfers and steps like that, but just make sure you go slow and trust what I call your ergo instinct. All right. Is this Markovnikov addition or anti-Markovnikov addition? Let's think about that. So check with your neighbor and see if you can determine whether or not this is Markovnikov. All right, let's see a show of hands. Who thinks Markovnikov? Who thinks anti-Markovnikov? All right, looks like we've got a majority saying Markovnikov. What does it mean when I say Markovnikov? The carbocation's more stable or more substituted, resulting in your nucleophile coming off of your more substituted carbon. So this one means that you get addition to the more substituted carbon. So in this case, this would be an example of Markovnikov addition because the alcohol is coming off the more substituted carbon, not the less substituted carbon. Does that make sense? All right, here's where it gets confusing. In lab last term, we did a reaction with cyclohexanol. You remember that? And you probably remember, because it was stinky, we made cyclohexene. What were the reagents we used to accomplish that transformation? Does anybody remember? We used sulfuric acid, and did we run it hot or cold? Hot. So we used concentrated acid. In this case, it was sulfuric acid, and then we ran this at a high temperature. The byproduct of this reaction was kicking off that alcohol, which ultimately became water, right? So that was the byproduct of that net reaction. What we're showing right now is kind of the reverse reaction. And the interesting thing that I said was that it requires catalytic acid. And would this be favorable under high temperature or low temperature? Okay, so say low or moderate temp. And this confuses students where they say, well, why is acid favoring one direction one way, but then acid is favoring the other direction the other way? Does anybody have an idea about the difference between these two pathways? Let's go back up and look in our mechanism. In our mechanism, we said we had an alkene, excess water, and acid. Did we have excess water during our cyclohexanol lab? Did we add water in? No. In fact, we didn't want water in. So in this one, we would say to get our alcohol installed, we want excess water. Up here, we want little, or actually no water. Right? So then the question is, well, why? The truth is that this is under equilibrium conditions. So we can control the position of the equilibrium by either adding water or removing water from the reaction mixture. How many of you remember Le Chatelier's principle from general chemistry? Few people? So Le Chatelier's principle says you can drive the position of an equilibrium by adding or removing reagents on either side of the equilibrium, right? So that will shift the equilibrium position. So if we flood this with a bunch of water, all of a sudden this pathway is going to be favored, right? Because you have excess water. However, if you don't have much water and you drive it with heat, then you can favor going that way. So we need to be very careful with describing these reaction mechanisms with excess water or no water. So the way we really do that as chemists is when you say concentrated acid, that implies no water. If we write catalytic acid, that typically just implies that you're dropping acid into a water mixture, right? So it's implied that there's going to be excess water around. So catalytic acid implies excess water. Make sense? It's a super subtle difference, but it's one that I know confuses a lot of organic chemistry students. All right, you want to try a challenge?
Do you have a question with this?
Yeah.
So during this whole reaction, we never added water to our cyclohexene. So where does that plus H2O come from?
So you're talking about this side?
Yeah.
So the reaction we just saw was going from this as our starting materials over to this as our product. And we said in this reaction, right, we were adding water in as a reagent. Where the reaction we did in lab, the reverse reaction, where we started here and went here, we didn't add water in, right?
Right. So there was no water.
Exactly. So it really just depends on whether or not you have excess water around, which direction things go. Good questions. All right, so let's try a challenge. So for this challenge, I think it's actually in your textbook. I'm going to throw us for another loop. All right, catalytic acid. However, there is no water. And I'll go ahead and give you the final product, but then what I want you to do is to help me figure out, all right, if there's no water, how in the heck is this product getting made? So let's try to propose a mechanism that might account for formation of the product as shown. So I'll give you a minute to work on this and then check with your neighbor. All right, just for the sake of time, let's try to walk through this. I want to make sure we have enough time to get through our main material today. Fastest reaction in chemistry, acid-base chemistry. So we could argue maybe in the first step, we protonate our alcohol, right? Seems reasonable. Like I said in the notes above, we have no excess water around. All right, so what do you think the next step could be? So I heard somebody say the water falling off. If we did that, we'd get a primary carbocation. Not great. Let's take a look at our previous notes, though. Up here, we had something similar, right? In this step, right up here, we had our pi bond steal a proton, right? So let's try that. Let's do a similar step with our proposed mechanism. All right, so in this next step, we'd say, well, what if this pi bond steals a proton? Would we have a positive charge where the red thing is, or where the green positive charge is? Which one looks more correct? The red. So we always want to form our more stable carbocation, so I'll put that there. We know that the hydrogen must have been added right there, right? Do we need to show bonds to hydrogen? No. So for the sake of simplicity, I'm just going to erase that because it's going to just complicate things, right? But if you want to draw it in, go for it. All right? What do you think could happen in the next step if there's no water around? Yeah, the alcohol could act as a nucleophile just like water did. So this can swing in and attack itself. Now, if we think about it, right, we're going to form a ring. 1, 2, 3, 4, 5, 6 atoms long, right? So it's going to be a ring containing 6 atoms. The first atom is going to be oxygen. So it's going to look like this, where we've got 1, 2, 3, 4, 5, 6. And if we look at carbon 6 over here, right? Carbon 6 with the positive charge also has 2 methyl groups coming off of it. Now it's starting to look a lot like our final product, right? Because our final product had a ring system with oxygen and it had 2 methyl groups coming off of it. The other important thing to remember is this proton is still hanging off of this alcohol, which means it's still going to be in that intermediate, right? We can't just show it magically disappearing. Well, you can, you just won't get points for it. That's a joke. All right. And then in the last step, you can show deprotonation. I will show you a trick that I often do, is just for simple deprotonations, just write minus H plus to indicate that we're removing a proton. The simple truth is, during this reaction, another equivalent of your starting material would actually act as your proton transfer agent. Does this make sense? So some of these look super duper scary. My hope and goal is to get you to the point where when I show you these somewhat scary looking reactions, you can slow down, stay calm, and just use your instincts to get you from starting materials to products using the basic trends we've learned. Yep.
I have a question, but I don't know if I'm thinking wrong, but wouldn't the double bond take the hydrogen without taking up water?
So your question is, can you just do this first?
No, the hydrogen of the carbon dioxide. That's the, I mean, the hydrogen would be alcohol.
Can the alcohol do what first?
Could the double bond take the hydrogen that's
Oh, I think I see. So you're saying, can it use that? That's not acidic enough for that step to occur. You have to have a stronger acid. That's a good question. Alcohols aren't very acidic, so we need a stronger acid source to protonate an alkene. Yep, great question. All right, so as you can see, this kind of looks a lot like our hydrohalogenation, where we form our more stable carbocation, and then we have our nucleophile attack in. Sometimes there's variations where you have to do proton transfers, as in this case. So make sure you just slow down and you watch out for your simple arrow pushing. All right, now I'll show you a problem. And I'll see who can spot it first. Let's do another practice problem. Let's consider this alkene. And again, we're going to use catalytic acid. What's the first step going to be? Yep. We're going to, just like we saw before, we'll protonate our water and make a hydronium ion. All right. Next step. Who remembers what the next step is with these reactions? Yeah, the double bond's going to take the hydrogen. All right, we know that we want to get our positive charge off of the more substituted carbon, right? Meaning we don't want to show the positive charge here. Primary carbocations are worse than secondary. So this must be our carbocation intermediate. Everybody following along so far? All right, what else can happen that we haven't really talked about a whole lot yet? Rearrangement, right? Over here, we've got a secondary carbocation. Secondary carbocations aren't the best. If we can rearrange them into something better, it'll happen, right? If we think about it, we've got a hydrogen right over here. We could take this entire hydride, meaning the hydrogen and its electrons, and we can slide that entire hydrogen over. That would give us a tertiary carbocation, right? And then water would be floating around still. We know we always have excess water in these reactions, so water in the next step would add into that carbocation. Let me label this too. We said that this switches from secondary to tertiary. And then after water adds in, we're almost done. What's our last step going to be? Deprotonation. So we, as chemists, typically like to show neutral products, not products with positive charges. So we get to our final product with our acid. Make sense? So the problem we've kind of been neglecting so far is this rearrangement, right? Rearrangements are kind of a hassle. Rearrangements can lead to complicated mixtures, and it can sometimes prevent us from getting to a product that we necessarily want. All right, so let's make some notes here. rearrangements can/will occur. Sorry, I shouldn't have boxed that. Everybody's like, my notes. To avoid rearrangements, use oxymercuration. Demercuration. Oh. So I'm going to even underline this in red. And oxymercuration demercuration is a completely different mechanism, one we haven't seen before. Does oxymercuration sound like a fun reagent to do, something you'd want to do at home in your kitchen sink? Why? Because it uses mercury. It's super nasty stuff. It's a neurotoxin. So typically this is done as a last resort to avoid unwanted rearrangement chemistry. All right, so let's take a look at what happens. All right, so this is a special reagent that we're going to be using. This is called mercuric acetate. It's just abbreviated as HgOAc2. That's the kind of shorthand name for writing out mercuric acetate. And the reason they draw it that way is this entire group, if you remember way back to last term, is called an acetate group. And we've got an oxygen attached here. So if we kind of smush the oxygen and the acetate group together, it's just abbreviated as OAC, and we've got two of them bonded to mercury, so we put them in brackets like that. All right, so in the first step of this reaction, this reagent will just pop off like that and actually decompose on its own. All right, so now it's decomposed. We've just split that bond in half. Mercury has a positive charge. Like we saw previously, pi bonds are good nucleophiles, right? Or decent nucleophiles, I should say. And with mercury having a positive charge, it's a pretty decent electrophile. So in this next step, our pi bond, as a nucleophile, is going to reach over and attack the mercury with the positive charge that's acting as our electrophile. What happens next is a little bit weird. We get this three-membered ring system that looks a heck of a lot like what we saw last lecture period, right? You remember where we had bromine forming a three-membered ring? We have a similar three-membered ring right here where mercury's formed two bonds to those carbons that used to be a part of the pi bond, right? Does that make sense? All right, the weird thing with this, let me slide this over a little bit, is we can show this a little bit differently where, whoops, this bond is super duper weak. All right, if we do that, we've got this weird resonance structure where this bond between mercury and the central carbon is so weak, it's kind of halfway bonded, halfway not bonded. So let's think about the hybrid structure here. So I'm going to draw the hybrid over here. Looks like this, where we've got a partial positive being shared by the mercury and the adjacent oxygen, or adjacent carbon, excuse me. Does that make sense? So it looks a lot like the bromonium ion that we were previously working with. All right, in the next step, what we can do is we can react this with water. Water as a nucleophile is going to want to find the best electrophilic site. So just like we saw with the bromonium ion, where bromine was in the three-membered ring, we're going to attack the more substituted carbon because that's the carbon with the partial positive charge. And then just like with the bromonium ion, we're going to break this bond and kick electrons back to mercury to give it its neutral charge. Sorry, let me slide this over just a smidge. And then in the next step, what do you think is going to happen? Do we like to show a charged product? Nope. So what we often do is we'll kind of clean this up. We'll just say minus H plus. And we'll get here. Does that make sense? So all we've done in this last step is removed one of these protons coming off of the water molecule after it attacked in. All right, so this is going to be an intermediate. So what does this mean? It means during this reaction, sorry, I'm going to zoom out so we can see it all. We mixed our alkene, mercuric acetate, and water, and we got this final intermediate out as one of our products. This is an organomercury compound. Organomercury compounds are super nasty neurotoxins. This is one reason this reaction is not super popular. However, we only use it in situations where we absolutely have to avoid rearrangements. All right. So now that we've got that intermediate, we can go on to step 2. Step 2 is a bit of hand waviness right now. We're going to use this new reagent we haven't seen before called sodium borohydride. It's a strong reducing agent, and all that's going to do is get rid of the mercury part via a reduction reaction. So basically this whole part is going to get removed by the sodium borohydride and get us to our final alcohol product. Does that make sense? So you don't need to know this mechanism. All right, so let's kind of summarize this, because we kind of broke this down pretty quickly. We started out with this alkene. We said that we're going to use HgOAc2 and water in our first step. And we said after that first step, we're going to get an intermediate that looks like this. Let me slide this over a smidge more. And in fact, I'm going to use those abbreviations right there. So we've got our ACO group bonded to the mercury. And then in the next step, we treat this with NaBH4, our reducing agent, to get to our final product. Sorry, let me clean this up. Does that make sense? Yeah.
Just makes sense for my, is this the only reagent that can do this? We don't know, we don't need to know how did it.
The sodium borohydride, is that the only reagent? It's not the only reagent, it's the most commonly used one. We'll cover reduction reactions later on this term, but for right now, just remember that this is a reagent used for the second step of the oxymercuration demercuration process. Does that make sense? I know it's frustrating me showing you a reaction saying we don't know the mechanism right now, but we just kind of have to trust it right now. It's kind of above the skill level for this course. All right, so the cool thing with this is we said this mechanism avoids unwanted rearrangements. So it's a pretty good workaround for that rearrangement problem that we saw up above, where the alcohol actually ended up adding to the tertiary carbocation after the rearrangement process occurred. Does that make sense?
What part of it specifically in here is making it avoid the rearrangement?
Yeah, that's a good question. So the question was, why is it not rearranging? Well, if we look at it, it's not really going through a true carbocation intermediate in the same way that the bromonium ion avoided a carbocation rearrangement. Instead, this view over here is a more holistic view where we have this three-membered ring. And because it's going through a three-membered ring, it's not a true carbocation and won't rearrange. So that's what's stopping it from occurring. So it's kind of a weird workaround. I don't know how they discovered this besides just mixing random stuff together and finding that it worked. So it's kind of a weird discovery. All right. There's one other thing I wanted to hit, and we're just going to briefly get into this. So let's take this alkene and let's try to add an alcohol in. And we've got two different sides of the alkene. We've got the red side and the green side. So far, we've really been focused on adding alcohols to the red side and not the green side, right? In this case, the alcohol could be a wedge or a dash. We have to worry about getting both. So in this case, we would get a mixture of enantiomers. Is this called Markovnikov or Anti-Markovnikov? Well, let's think. Is the alcohol going to the more substituted position? Yeah, is that Markovnikov or anti? It's Markovnikov. Yeah, so this would be Markovnikov addition. Meaning it's adding to the more substituted carbon. And we actually have two different ways to get there. The first way we saw was H plus and water, right? So our catalytic acid and water pathway, that one seemed to make a lot of sense. And then we also saw that we still get the more substituted alcohol using oxymercuration demercuration. So the one we just saw, even though it's more toxic, would also work for this situation. So step one was that mercuric acetate and water. Step two was sodium borohydride. Both of these would give you the Markovnikov addition product. Which one would you prefer to do as a chemist? Top one. Why wouldn't you do the bottom one, even though the bottom one avoids rearrangements?
There's 2 steps.
Well, there's 2 steps. I don't like doing more work. I agree with that. Can this rearrange? No, it won't rearrange. So the top pathway is going to be the better pathway. It's not wrong to do the bottom one. It's just not environmentally friendly and it's more work, right? So either pathway could work, but the top pathway in this example works better. So let's think about how we get to anti-Markovnikov products. All right, so chemists worked on this for quite a while. And the cool thing with this is they found a reagent that worked spectacularly well. So the reagent that they use in the first step is BH3. That's borane. Sorry, that's not a very good 3. Do you remember me talking about borane a lot last term? What's unique about it? Empty p orbital, right? So if it has an empty p orbital, that means it's a really, really good electrophile, right? So because it's a good electrophile, it wants to react with double bonds very, very quickly because double bonds are good nucleophiles. The problem is you can't just buy borane by itself. It's impossible. It always comes with some sort of solvent. So oftentimes you see it with a dot THF. That just means that THF is the solvent that it's being mixed with when they sell it to you. All right. So in this first step, it's kind of neat. And I'll show you next, but the borane will attach to the double bond. And then in step 2, you react it with hydrogen peroxide and sodium hydroxide. So just like we saw before, we've got the red position, that's Markovnikov, green position's Anti-Markovnikov. In this one, we're not going to add to the red position. Instead, we're going to add to the green position, and we're going to get an Anti-Markovnikov alcohol. All right, so question is why? Why does this work? I'm not going to go through the full mechanism simply because it takes way too long, but I'll show the really brief tutorial. So over here what happens is we have borane. Looks like this. Borane will get really, really close to that pi bond. And when this happens, the pi bond is going to attack the boron. Whoops, let me kind of show that better. Like that, and coordinate with the empty p orbital. And then at the same time, the entire hydrogen group is going to shift over to the less substituted side. So the question is, well, why would boron prefer to be off of the end rather than in the middle? Does anybody have an explanation for that? I see Hunter gesturing with his hands. I think he's close.
More crowded.
It's more crowded, right? So the boron has an easier time docking off of to the side where it's more open and accessible than it does in the middle. So after this process is all said and done, in the next step, we oxidize this using sodium hydroxide and H2O2. This entire portion is going to be replaced with an alcohol. So we can swap that off with an alcohol in one step. So I'm just going to write here, you don't need to know the mechanism. At least I don't expect you to know it. However, what I'll do is I'll post a supplemental video online where if you are curious, if you're just the type of person that wants to know how these steps all work, you can watch it. It's just, I tried it one year and it took me a whole lecture period just to do that last arrow pushing step. So I just decided it's not worth our time, but you can watch it at home. Does that make sense? All right.
Is this part on the exam?
The mechanism?
Yeah.
So this mechanism right here and this one right here won't be on the exam. But what I could do is I could say, all right, fill in this box here, right? So kind of like we're used to on our exams, I could say either give me the reagent required for this transformation or show me the product at the end of the transformation. All right, so that's where we're going to end today. Make sure over the weekend that you start your skill builders. They pile up quickly, so try to do a little bit every day so they're not super overwhelming, and then feel free to email me if you get stuck. You can send me cell phone pictures or just describe it to me via email, and I can try to help you on problems you're stuck with.